All right, the next property for binomial coefficients. So let m and and r be non-negative integers. With r less than equal to minimum of m and n. So r has to be less than equal to both m and n. Then we can say that m plus n, choose r, is equal to sigma m r minus k times n, choose k, and then k from 0 to r. Okay, so well, this one in previous properties, we saw both two types of proofs: algebraic proofs and proof and combinatorial proof. And some cases, algebraic proof at least looked easier to manage. But this one, for example, if you want to do the algebraic proof, see, you have to expand the right-hand side, and then there you'll have one expression for this, m factorial over some denominator times this, and then you have to add all of those together and get common denominator between all those numbers. So it's going to be a little bit lengthy and messy and hard to handle, right? But with combinatorial proof, we can easily prove this property. So proof, combinatorial proof. So consider a set S, let's say, for example, A1 to AM, and T equals, let's say, B1 to Bn. So let's consider two sets, one set with m elements and one set with n elements. So let's consider sets. Then m plus n, choose r. Left-hand side is m plus n, choose r, is the number of ways to choose a set, let's say A with r elements out of elements of S union T. S union T will have m plus n elements. And if you want to choose r elements out of m plus n elements, so by the way, if I want to be sure that S union T has m plus n elements, so let me also say with S intersection T equals empty set, because I mean, S has m elements, T has n elements, so S union T will have m plus n elements as long as S and T are disjoint sets, right? So with this assumption, S union T will have m plus n elements, and if I want to choose a set with r elements from S union T, then there are m plus n choose r ways that I can do this, and I can choose a set with r elements out of elements of S union T. Okay, now this is the left-hand side. What about the right-hand side? How can I make a connection with right-hand side? So note to choose a set A with r elements we can also choose a set, let's say P with k elements out of S and a set C with R minus k elements out of elements of T, and then set A equals B union C. Right? See, you have S here and T here, M elements here, and N elements here. So if I want to choose R elements from S union T, I can choose K elements here and R minus K elements here. So I'm calling this one B, and then C, and then B union C will contain R elements, which I'm calling it A. Okay. So, and what is the condition on K here? So by the way, K has to be some number less than equal to R and bigger than equal to 0, right? So with K bigger than equal to 0, less than equal to R. So if I choose a set B with K elements, C with R minus K elements, then I combine them, then the resulting set will have R elements, which is my set A. Okay, so what am I saying here? I'm saying that to perform the task of choosing a set A with R elements, equivalently, we can decompose these tasks into two smaller tasks. First task, choosing K elements from a set S, and second task, choosing a set with R minus K elements from a set T, and then combine them. So by product rule, we know that if for task 1, we have N1 ways to do it, and task 2, N2 ways to do it, then combine, we have N1 times N2 ways to perform the combination of those tasks. So here, now to choose the set B as described above, we have S had how many elements? S had M elements. So M choose K. But if I want to be consistent with the theorem that I wrote, so because I said M choose R minus K, so let me say then K elements out of T here, and the other one out of S, just to be consistent with what I mentioned as a theorem. So now to choose the set B as described above, we have N choose K ways to do so. To choose the set C as described above, we have M choose R minus K ways to do so. So by product rule, we have sigma n choose k times m choose r minus k, k from 0 to r, ways to choose the set A, which is B union C. Okay, so for a fixed value of k, if k is a fixed value between 0 and r, then we have n choose k times m choose r minus k ways to choose B union C for a fixed value of k. But k itself can change between 0 and r. So I have to write the expression corresponding to k equals 0, then add it with the expression with k corresponding to k equals 1, and so on. So in total, I will have this many ways to construct a set A with R elements. Okay, so the first term of the sum corresponds to k equals 0, second term of the sum corresponds to k equals 1, and so on. The last term corresponds to k equals R. Okay, so that's all. And now let's look at, so this is called Vandermonde identity, by the way. So the name of this identity, I mention it here, Vandermonde identity. And the corollary of this, corollary of 5, is that if n is a non-negative integer, then 2n, choose n, is equal to sigma n choose k to power 2, k from 0 to n. So proof, you apply 5 with m equals n equals r. So m and n and r, all of them, let's set it to be equal to n. What do we get then? M, so look at the identity 5. Now m and n and r, all of them equal n here. So it's going to, the left hand side is going to be n plus n choose n, which is 2n choose n. So left hand side with 2n choose n. Then left hand side equals m plus n choose r equals n plus n choose n, 2n choose n. And right hand side will be sigma, what was it, m choose r minus k, n choose k, k from 0 to n. But m and n are equal here, so n, r is also n, so n minus k, n k, n choose k, k from 0 to n. By the way, one of the properties we saw before, we know that n choose k is same as n choose n minus k. So then I can write this one as k from 0 to n choose k times n choose k. This is sigma k from 0 to n choose k to power 2. Okay, so which is what we needed to show. All right, so this is about 6.4, and then now let's move on to 6.5, generalized permutations and combinations. So first, let's look at the permutations with repetition. Okay, so in the standard permutation and combination, we do not allow repetition, right? So for example, when you say you want to choose 2 members of the class to be to form a committee, let's say. So of course, those 2 members are not allowed to be the same student. You cannot choose student 1 and student 1, right? So student 1 is just one person. Then for the second person, you have to choose another student. But what about if we want to allow repetition? Of course, for that example, it doesn't make sense to allow repetition, because then we'll have 1 student, not 2 students. If you want to have a committee with 2 students, but you cannot allow repetition. But in some cases or some examples, we have to allow repetition. So let's look at an example. How many strings of length r can be formed from the letters of the English alphabet. English alphabet. From the uppercase, letters of the English alphabet. Okay, so we want to form a string of length r, so 1 letter, 2 letters, up to r letters. And for the first position, how many choices do we have? So here we could have, because we want to have uppercase letters, so capital A or capital B, right? Or all the way to capital Z. So we have 26 choices. Again, similarly, because see here the repetition is allowed, because it doesn't say that the letters must be different, right? It doesn't say that. It just says that you just want to have a string of length r, so you just want to put r letters next to each other, and all the letters must be in capital or uppercase, and that's all the restriction you have. And repetition is allowed. You're allowed to have same letter repeated, and you can put the same letter next to each other. So again, for the second position, you have again A, B, all the way to Z. Again, 26 choices. And all the way here, we have again same 26 choices. So again, by product rule, we have 26 times 26 times 26 r times, which means 26 to power r choices to form a string of length R using uppercase letters. Okay, so same idea can be applied for the general case. So we can say that theorem, the number of R permutations of a set of n objects with repetition allowed is n to power R. So same idea, instead of 26 and R, we can do the same idea. When you want to choose R objects out of n objects, and repetition is allowed. So it's the proof is exactly what we said. Instead of 26 choices, you have to write n choices, right? Again, you have R positions for the first position, you have n choices for the second position, you have n choices because repetition is allowed, right? All the way for the rth position, you have n choices, and in total, you will have n to power R choices, right? So proof, let me leave as exercise because I wrote the proof for you. You just need to replace the number 26 with n. The idea is exactly the same. Okay. Now, this is about permutation with repetition. Now let's look at combinations with repetition. So example, suppose that you want to choose let's say four fruits from a bowl of fruits that contains let's say six fruits from a bowl of fruit that contains four types of fruits. Four types means oranges, apples, and banana, and let's say grapefruit. So four types. And you want to choose six of them. So in how many ways can we choose our six fruits? Six fruits. So here, see if you compare with the previous cases of examples of combinations where we said, for example, 6 students are to be chosen to form a committee. So none of the students are going to be repeated or allowed to be repeated. But here, when we say 6 fruits, I am allowed to have 2 oranges or 2 apples or 3 apples, right? So I can have repeated oranges or repeated apples here, for example. So how can I find the total number of ways to choose 6 fruits out of a bowl of fruits which contains 4 types: oranges, apples, bananas, and grapefruits. So I want to say that this is equivalent with saying that with the number of solutions of a certain type of equation. So let me say, let me write it this way. Let x1 denote number of oranges. Let x2 denote number of apples. Let x3 denote number of bananas. And let x4 denote number of grapefruits. Okay, now each choice of 6 fruits corresponds to a solution of the following equation. x1 plus x2 plus x3 plus x4 equals 6, with x1, x2, x3, x4 being non-negative integers. Right? So each solution of this corresponds to one choice for us for choosing 6 fruits, and each choice of us for choosing 6 fruits corresponds to one solution of this equation. So let me give you an example. For example, let's look at the solution of this equation. So this is an equation with 4 variables. So you, in the beginning, in the first sight, you may think that, this equation has infinitely many solutions because just one equation with 4 variables, but that's not the case, because yes, it has 4 variables, but yes, if all the 4 variables were allowed to be any real numbers, then we would have infinitely many solutions. But each variable here is only allowed to be a non-negative integer. So one equation with more than even one variable, as long as the variables have some restrictions on them, in this case being non-negative integers, may have finitely many solutions. In this case, it has finitely many solutions. If you have an equation with few variables, and right hand side is a fixed positive number, and the left hand side you have few variables and each of them are supposed to be non-negative integers, then you will have finitely many solutions, not infinitely many solutions. And I'm saying that each of those solutions correspond to one choice of us for choosing those 6 fruits. So let's look at, for example, let's say if I say, let's look at one solution of this. Tell me one solution of this equation. For example, let's say x1 equals 3, x2 equals 1, x3 equals 2, x4 equals 0. This is a solution for this equation because 3 plus 1 plus 2 plus 0 is 6. And this solution for this equation corresponds to one choice of us for choosing 6 fruits. Why? Because when we say x1 equals 3, x1 equals 3, x1 denotes the number of oranges. So that means, so this corresponds to choosing 3 oranges x2 equals 1. x2 is the number of apples, so that means I am choosing 1 apple. x3 equals 2 means I'm choosing 2 bananas. And I'm choosing 0 grapefruits. And in total, I will have 6 fruits. Okay, so this is one way to choose 6 fruits. 3 oranges, 1 apple, 2 bananas, 0 grapefruits. Or the other way around, if let's say, so if I have a solution for my equation, I can correspond it to a choice for choosing 6 fruits. And also, if I have a choice for choosing 6 fruits, a specific choice for choosing 6 fruits, then I can correspond it to one solution of this equation. So for example, choosing 4 oranges and let's say 1 apple and choosing 1 banana, choosing 0 grapefruit corresponds to x1 equals 4, x2 equals 1, x3 equals 1, x4 equals 0, which is a solution of the equation x1 plus x2 plus x3 plus x4 equals 6. Okay, so what can we conclude? We can conclude that to answer this question, we have to count the number of solutions for this equation, x1 plus x2 plus x3 plus x4 equals 6. If I can count the number of solutions for this equation, that means that number is the number of ways I can choose 6 fruits, because each solution corresponds to one choice of the fruits, and each choice of the fruits corresponds to one solution of this equation. Okay, so this means hence we must count number of solutions of x1 plus x2 plus x3 plus x4 equals 6, and the number of solutions will be the same as number of ways to choose 6 fruits. Okay, now let's look at the number of solutions for x1 plus x2, let's say plus xr equals n. So theorem, let n be a non-negative integer, and let r bigger than or equal to 1 be a positive integer, then we can say that the number of solutions of x1 plus x2 plus dot 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 plus xr equals n is given by n plus r minus 1, choose r minus 1. Seems the screen is freezed. Let me stop share. Okay, so let's see. Okay, I'm going to prove this for you, but before proving it, so back to example above, we can say that number of solutions of x1. What was the equation? Do you remember? x1 plus x2 plus x3 plus x4 equals 6. By theorem above is given by 6 plus 4 minus 1. Choose 4 minus 1. So this is 9, choose 3. And how much is this? 9 factorial over 3 factorial, 6 factorial, 7 times 8 times 9 divided by 6. So this one is 3, 3. So divided by 3 will be 2. And then this one 2 divided, 8 divided by 2 is 4. And 12 times 7, that's 84. So we'll have 84 ways. 84 ways to choose six fruits of 4 types. Okay, so in total we have 84 options to choose our 6 fruits. So for example, one option is that we choose all 6 of them, let's say apples. One option, let's say 5 apples, 1 orange, or 5 apples, 1 banana, or all 6 banana. So you can see that there are so many options. In total, we have 84 options. We have 4 options to choose, 4 types of fruits, but 84 ways to choose 6 fruits in total from those 4 types. All right, so now let's prove the theorem, proof of theorem. So we want to show that the number of solutions for this equation is given by n plus r minus 1. Choose r minus 1. So I'm going to consider, n plus r minus 1 bars in the following form. So see 1, 2, 3, 4, n plus r minus 1. So if I choose r minus 1 bars, r minus 1 bars out of this many bars, so then any choice of r minus 1 bars from the bars above corresponds to one solution of the equation x1 plus all the way to xr equals n. So why does it correspond to one solution of this? So x1 is equal to number of bars before the first selected bar, x2 equals number of bars between the first and second selected bars, x3 equals number of bars between the second and third selected bars, and all the way to xr equals number of bars after r minus first selected bar. So also conversely, any solution of the equation x1 plus dot 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 xr equals n corresponds to one choice of r minus 1 bars out of n plus r minus 1 bars above the first selected bar will be x1 plus first bar. The second selected bar will be x1 plus 1 plus x2 plus 1 bar and so on. So the r minus 1, r minus first selected bar will be x1 plus all the way to xr minus 1 plus r minus 1 select bar, r minus first bar. Okay, so I'm going to explain this. I know it could be a little bit confusing. I'm going to explain this with a simple example just to make the idea clear. So we show that any solution of this corresponds to one choice of r minus 1 bars out of n minus n plus r minus 1 bars. So that means, hence, number of solutions for x1 plus all the way to xr equals n is number of ways to choose r minus 1 bars out of n plus r minus 1 bars, which is given by n plus r minus 1, choose r minus 1. Okay, so let me explain the idea with a simple example. Let's say if you want x1 plus x2 plus x3 plus x4 equals 6. So you want to count number of solutions where you know x1, x2, x3, x4 are all bigger than or equal to 0. So you want to count number of solutions for this equation. How can I do that? So the idea here, we are saying that, so here n is 6, r is 4. So the idea is that you have to consider n plus r minus 1, which is 9 bars. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bars. And we are saying that if you choose 3 bars out of these 9 bars, then you will have a solution for this equation. And each choice of, and if you change the 3 bars that you select, then you get a new solution for this equation. So look at here. If I choose 3 bars out of these 9 bars, let's say any 3 bars, let's say this one, for example, and this one, and this one. Then I will have a solution for my equation. How so? So x1 is going to be the number of bars before the first selected bar. So see, I have 2 selected bars before the first, my first selected bar, which I circled with red, is this one. The bars before that is this one. So this is, that means x1 is 2 because I have 2 bars before this. x2 is the number of bars between first and second selected bar. So x2 is 1. There's only 1 bar between first and second. Between second and third, there are 2. So x3 equals 2. And after third bar, I have only 1 bar. So x4 is 1. So this choice of selected bars, so if I choose my bars, 3 bars this way, then I will have this solution for my equation. And of course, this is a solution x1 equals 2, x2 equals 1, x3 equals 2, x4 equals 1 is a solution for this equation, right? Because 2 plus 1 plus 2 plus 1 is 6. Now, if I change the 3 bars that I select, the solution will also change. Let me give you an example. Let's say again, I draw this same 9 bars, but let's say this time I choose another 3 bars and circle them with red. Let's say if I choose these 3 bars this time, let's say, then this corresponds to another solution of my equation. How so? The solution corresponding to this choice of 3 bars is what? Well, this is the first selected bar. x1 is, according to what we said, x1 is the number of bars before the first selected bar. How many bars do you see before the first selected bar? But there is no bar before the first selected bar, so that means x1 is 0. x2 is the number of bars between first and second. There is nothing again, so x2 is also 0. There is no bar between first and second. x3 is the bars between second and third, so 1, 2, 3, 4, so x3 is 4. And x4 is the bars after the third selected bar, so x4 is 2. See, 0,042 is also a solution for this. Is 0,0,0, 0 plus 0 plus 4 plus 2, that's also 6. So as you can see, each choice of 3 bars out of these 9 bars will lead to a new solution of my equation. So that's what I said here. See, we said that any choice of r minus 1 bars from the n plus r minus 1 bars above correspond to one solution of this equation, where x1 is the bars before the first selected bar, x2 between first and second, and so on. We also said that, so if you fix the choice of r minus 1 bars out of n plus 1 r n plus r minus 1 bars, then you will have a solution. Conversely, if you fix a solution for this equation, that solution also corresponds to choosing r minus 1 bars out of n plus r minus 1 bars. For example, here, let's say if I fix, so previously I started with choosing 3 bars, then I found the corresponding solution. But this time, let's say if I start with the solution, let's say if I start with the solution x1 equals 2, x2 equals 1, x3 equals 2, x4 equals 1, then this solution will correspond to one choice of 3 bars out of 9 bars. How so? If x1 is 2, then the first selected bar is going to be in the position x1 plus 1, according to what we said here. So when you see here, we said the first selected bar will be x1 plus 1, x1 plus 1 bar. And then the second selected bar, x1 plus 1 plus x2 plus 1 bar, and so on. So if x1 is 2, the first selected bar is 2 in the position 2 plus 1, which is 3. The next selected bar in the position of x1 plus x2 plus 2. So that's going to be 2 plus 1, 3 plus 2, 5. So 1, 2, 3, 4, 5. And then the next one, you can see that is the position 8, and so on. So, or in this example, if you start with the solution, x1 equals 0, x2 equals 0. So the first bar is in the position x1 plus 1. If x1 is 0, the position will be 0 plus 1, which is 1. Second selected bar is going to be in the position x1 plus x2 plus 2. So that's going to be 0 plus 0 plus 2. That's going to be 2. Second selected bar, and so on. So what did we show here? We showed that there is a correspondence, one-to-one correspondence between the solutions of this equation and choosing r minus 1 bars out of n plus r minus 1 bars. If I choose r minus 1 bars, then that choice will correspond to a unique solution of this equation. And if I start with a unique solution of the equation, that corresponds to a unique choice of r minus 1 bars out of n plus r minus 1 bars. So this means there is a one-to-one correspondence between the solutions and choosing r minus 1 bars. Well, and I, of course, know that to choose r minus 1 bars out of n plus r minus 1 bars, I can simply use combinations, and that can be done in n plus r minus 1, choose r minus 1 ways. Well, that means that the number of solutions is also the same number. Okay, so this is an important result in, we can say, both discrete mathematics and combinatorics. Also in number theory, because, you know, when you deal with numbers and equations, we deal with equations where the variables takes values from the set of integers or positive integers. So that's considered a problem in number theory. So this is a very important result, and it has lots of applications. Well, one application we saw that we want to choose, for example, 6 fruits of 4 types. In how many ways can we do that? But of course, we can give so many more applications for this type of equation. And maybe next time I can give you a few more examples or applications for the number of solutions of an equation of this type. Okay, guys, so thank you, and see you next time.